Welcome to part 2 and the last part of 3.11, where we're going to be talking about vector spaces and subspaces, but specifically focusing on the first two fundamental vector spaces, known as the column space and the row space, specifically for matrices. And so we're going to focus on a matrix A that is an M by N. So we are looking at a rectangular matrix specifically. Now column space we've been talking about since Unit 1, so we're not going to dive too much into it outside of when we're looking at the column space of A, we're looking at all of the linear combinations of the columns of A. And when we've done this in the past, we've been doing it under the lens of looking at this system and this equation and trying to solve it, where if we're trying to solve for what X will give me B as a result, what this column space is doing is looking at all of the possible combinations that we could use for X and all of the possible values or vectors for B that we could achieve. And the only time that this would have a solution is if B is in that column space. Because again, when we talk about the column space for a matrix A, we're looking at the linear combinations of all of the columns, and that's what AX is doing. Remember, when we look at this in terms of the column picture, we're taking all possible combinations according to the entries in X, X1, X2, all the way down, and taking all possible combinations and figuring out what combination can get me to B. And if B is not in this space, then there's no way to solve that problem. And so we could say that B is in the space of the column space of A when we were solving, and which we'll get into a little bit more later on. The key, though, is that these are focusing on the linear combinations. So it's all about adding, subtracting, multiplying by scalars. Again, like we talked about in that first video, looking at combinations like this, D times W, where this can now be multiple vectors across the board, A1, A2, A3, where this is X1, X2, X3, all the way down. And because we're looking at it in, as those columns, we're focusing in our M. So when we look at our overall space, we're focusing in this dimension. Looking almost in terms of the rows, the number of equations that we have, but in terms of my combinations. And when we're doing this, and we'll highlight this a little bit more at the end of this video in particular, is that when I take all of these combinations, what these combinations are essentially giving me is what's referred to as the span of the column space of A. Because again, the column space contains every possible combination of the columns. And in linear algebra, what we say when we're talking about all of those different possibilities is we span that space. The book, and what I kind of want to emphasize a little bit, is that the individual columns themselves, so if I don't do any combination, but I just focus on the individual columns, that does not equate to a subspace. What equates to a subspace is the span in all of the possible linear combinations of those columns, and this is then a subspace of Rn, if I look at all of those possibilities. And so that's where that subspace language kind of begins to kick in. Now, where this comes into play in terms of row space is we typically want to think about our matrix in terms of columns. And so if I want to now look at my rows of my matrix, again, if I'm thinking about my matrix now and I want to look this way instead of vertically, recall from the previous unit, even towards the end of it, that if I want to think about these as columns, I can by transposing this matrix. I can now take these rows and turn them into columns. And so when we talk about row space, we're actually still talking about a column space, but we're talking about the column space of the transpose of A. And then we're following the same format that we talked about here. We're looking at what are all of the possible combinations of these columns, which is essentially the same thing as the combinations for my rows of A. And this will now create a subspace, but this time in regards to Rn, because now we're focusing, as we flip this, n, the number of columns I have here, becomes my rows and the number of equations that we have for a rectangular matrix. If it's square, then these two things would essentially be the same. But now, all of these columns in the transpose will span the column space, and now this column space, or the row space of A, is now a subspace of Rn. Both of these would contain the zero vector, because as I go through with all my possible combinations, we would then be setting up a solution like this, or essentially a solution like this, and going through and solving, so the zero vector is included between these, and so all of the criteria is met that we discussed in the first part of the video. He talks about and mentions rank. We did that all in Unit 1, so I'm not going to focus about that. Instead, I just kind of want to highlight a little bit more about this word span, because this is definitely a newer word. I'll grab the eraser. And just do a little bit more emphasis on it before we kind of get a lead in into what the next section is in the next video. This part is fairly short. Is around just the word span, and specifically we talk about the columns of A span the column space of A. Because again, when I take this entire space, what this space represents is all of the possible combinations of the columns. Well, again, linear algebra, when I'm looking at the linear combinations, we refer to this as spanning something. Spanning a space, spanning a subspace, etc. And so he gives a couple of different examples, as well as a couple test questions that I would encourage you to take a look at. But specifically, if we look at all possible combinations and we call that a set of S, so this again is the list of every possible vector that we could create by taking the columns of A and doing linear combinations, this would be a subspace of V. Or essentially, we would have a vector space from this. This would create a vector space when we take all of it, V. We say that all of these possible combinations would span this space. Again, I think of like the word span, almost like again, if you were to take a fan and unveil it, the dimensions of that fan and the angle of that fan span over a certain area. We can do the same thing in terms of a room, et cetera, with vectors and locations and area. So with that saying, he gives them a couple of examples. I'll leave that there. What I was going to highlight then was the next fundamental space, which is the null space. So when we are looking at now no longer AX is equal to B, but AX is equal to 0. So all solution sets to this, if I was to take all possible combinations for that solution set, that would give us the null space, and it would span that space. And so this is where we're going to be heading into next. There's going to be a couple new things that's going to actually require us to solve a system, because we actually need to solve this to create what those possible combinations are. Because unlike column space, where we're just taking those individual columns and doing combinations on them, we didn't have a specific B, right? The idea was B is the result of being within all of those possible combinations. Well, now we're saying, okay, well, this system is equal to 0, so what would actually make that 0? Is that the 0 vector, or are there some free parameters? Are my columns linearly dependent versus independent? All of that will kind of come back. We will, just in terms of a preview, go back to our factoring method into C and R. So we'll go back and kind of review that. So if you need to review that before we hop into the next video and lesson, please do that. And as always, if you have any questions, shoot me an email if you were on the online class. So hopefully it kind of helps identify a couple things with column space, row space, as well as just what the word span means. I know it's kind of to the point. This video is meant to be a little bit shorter just because it's a little bit more terminology, and we've also been playing in this realm pretty much for the first 2 units, which is fantastic. But just kind of helps identify those key terms. So with that, I bid you adieu.